Welcome back. So we were talking about the smooth functions and how useful they are in terms of studying the performance of optimization algorithms for non-convex problems, and also the fact that smoothness helps us to understand gradient descent from a new perspective, a perspective that could be useful when designing new algorithms or more advanced algorithms. In this video, we're going to talk about the proof of the theorems we stated for functions that are smooth but not necessarily convex, right? So recall we said that if I denote the initial suboptimality by delta for gradient descent, we have this specific result, which essentially says that the expected norm of the gradient is bounded by a certain bound which approaches 0 with this rate. For SGD, we say that the expected gradient norm, again, is bounded by another bound, which approaches 0 at a slower rate. Okay? So let's talk about the proof of these theorems. So first, I'm going to talk about the proof of the first theorem, and then we're going to see what kind of modifications we need to make to that proof to prove the second theorem. Okay? All right. So the key idea is, again, to study the amount of progress we are making, and our friend here is a smoothness. So we're going to leverage the fact that the function is smooth. Okay? In particular, as we saw in the previous lectures, smoothness helps us to understand progress. Okay? So helps us to actually study the progress we are making, because we have this very nice convex quadratic upper bound on the function. So we can actually use that here. So all I'm doing here, I'm using the definition of a smoothness when x is basically wt and y is wt plus 1. Again, the idea is that this helps me to understand the progress I'm making while running gradient descent. Okay? So this holds for any wt and wt plus 1. These are not arbitrary. We are using this specific update to go from one solution to the next one. So I'm going to leverage it here. Okay? So in particular, I'm going to replace the difference between wt plus 1 and wt with eta, the learning rate, times the gradient. Okay? So that enables me to go to this line. So this difference is basically becomes just the gradient times the learning rate. Okay. Now I'll do some rearranging to basically find what's the coefficient of the gradient norm square, and note that this inner product is basically norm square. So if I, let's say, give what's the inner product of x and x, this is essentially saying that what's x times x, and that's x squared. So this is the norm of x squared. Okay? In this case, x is the gradient. All right. Now, therefore, what does this result say? It says that the progress is basically the norm of the gradient square times another term. Okay? So before proceeding with the rest of the proof, I want to state a few remarks. So first of all, we see here that the progress depends on the norm of the gradient square. What does that mean? It means that the larger the gradient, the more progress we are making, right? And this is very, very nice. So it means that if you are very far away from the solution, so let's say, let me use another color. So let's say this is the function you are minimizing. When I'm here, I'm going to make more progress. But then when I am approaching the solution, maybe I'm going to be a little bit more refined in how I'm progressing. So the progress is going to automatically shrink as the norm of the gradient starts to go down. Okay. Another important side note is related to the role of the learning rate. as long as the learning rate is less than, strictly less than 2 over L, we are guaranteed to make progress. Okay. And this is actually something which has been sort of observed in deep learning, that and this is called the edge of instability. Okay, because if the step size goes beyond this, the optimization becomes unstable, and you may end up actually maximizing the function, right? So you're not going to make any progress at all. And it's been observed to be a relevant phenomenon when optimizing parameters of a deep learning models. And the last side note here is that, okay, so we're talking about the progress, and as we mentioned before, we want to make sure that we are maximizing the progress. Okay, so if I treat the progress as a function of the learning rate, the maximum progress will happen when the step size is exactly 1 over L. Okay, so this is a quadratic function. You can easily optimize it by taking the gradient and set it equal to 0. Okay, and this is indeed the step size that appeared in the statement of the proof. So essentially, the best constant step size is 1 over L, because that ensures we are making the maximum progress in each iteration. With that, let's carry on with the rest of the proof. And the rest is actually almost trivial. We're just going to do some rearranging and then take the average over time. This rearranging requires us to make this assumption because we're going to divide by some factors, notably this part. And if this is if the step size is larger than 2 over L, this factor will be negative. So therefore, the direction of our inequalities are not going to be the way we want them to be. But after rearrangement and taking the average, we notice the telescoping structure that I see here in the numerator. So I have, let's say, f of W1 minus f of W2 plus f of W2 minus f of W3, etc. So all of these terms in the middle will cancel, and then I'm going to be left with the first term minus the last term. Okay, so essentially something like this. And this is something we saw before as well. Okay, now we're going to note that whatever WT plus, sorry, this has to be capital T. Whatever WT plus 1 is, its function value is more than the optimal function value. So I can replace it with f at W star and get an upper bound. And this is nothing but the initial suboptimality that we defined and appeared in the statement of the theorem. Okay, and with this, with noting that we can apply this fact, we're going to arrive to this bound that holds for all learning rates that are strictly less than 2 over L. So as long as eta is strictly less than 2 over L, this bound is satisfied. This is a function of the learning rate. We optimize it to get the minimum bound. And it happens that the minimum is attained when the step size is 1 over L. And therefore, we're going to establish the statement, stated results. Okay, so that's the proof of the first theorem. Very, very easy. All that it required was for us to leverage a smoothness. And basically, nothing more complicated than that. Now let's talk about the proof of the SGD method. And it shouldn't be a surprise that we're going to follow a very similar approach. Okay, so we're going to again use a smoothness to study the progress, and then we're going to leverage the update of the SGD algorithm instead of gradient descent. Now things become a little bit more problematic or more complicated when we do so, because SGD by nature is a randomized algorithm. So the random decisions we've made in terms of selecting the mini batches or samples to find the stochastic gradient are going to determine the performance. So we need, in particular, or more mathematically, the solution at time t, wt, and the stochastic gradients are random quantities. So we need proper expectations, something we saw before when we talked about the proof of stochastic gradient descent on Lipschitz and convex functions. And therefore, we also need some assumptions on how good our estimators are. In particular, we're going to again assume that we have access to a stochastic first order oracle, which provides unbiased estimators of the true gradient with bounded variance. And finally, for the ease of analysis, we're going to assume that the samples are independent. With these, we can easily carry out with the rest of the proof. Okay. So like before, we're going to condition on the current solution, which again is equivalent to conditioning on the previous selection of the previous samples. And the reason for that is that I want to single out the impact of randomness arising from selection of ZT, the mini batch I'm using at time t, and use the unbiasedness property of my stochastic first order oracle. So we're going to take this conditional expectation. Again, I can use linearity of expectation to change the order of expectation and inner product. And finally, the term here is nothing but the gradient at wt because I'm using an unbiased oracle. And finally, this is nothing but the norm of the gradient x squared, because I have gradient inner product with itself. Okay. Right. So this is basically our way of handling this term. Okay. Now we're going to need to handle this term, but we're going to use a similar approach. Okay. So we're going to again condition on wt. We're going to add and subtract the gradient, again, because I want to leverage the fact that my stochastic first order oracle is unbiased and has bounded variance. And again, this is something we saw before in the proof of SGD for convex and Lipschitz functions. So we're going to arrive to this point by using the unbiasedness assumption of our oracle. And finally, by noting that the oracle provides bounded variance, we're going to arrive to this point. Okay. All right. So what did we do? So we had some bound on the progress. There were two terms that we needed to handle them, and we did that by taking proper expectations, right? Now, therefore, this is the result that we have. The expected value of the function at the next solution is bounded by the current function value minus this term plus a third term. The first term and the second terms are identical to what we saw when we were analyzing gradient descent. And we basically use that to note, as long as the step size is strictly less than 2 over L, we are making progress. Okay. In this case, however, given that we are using random estimators, and given that this last term is not necessarily 0, what will happen is that we're not going to have any guarantee on the expected progress anymore. So what does that mean? It means that if you run we run SGD, maybe the next solution is actually worse than the previous one. That's why typically there are some variations like this when you are minimizing the training loss. So if this is the loss, and this is, let's say, t, there are ups and downs when we are using algorithms based on SGD, right? So because we don't necessarily have any guarantee on the progress, given that our algorithms are using these randomized operations to estimate the true gradient. Okay, so this is the side note, But after this, the rest is again identical to what we saw before. So we're gonna take average over time, do some rearranging. Again, this requires that the step size is less than the edge of instability, 2 over L. And then finally, we have to take expectation with respect to all of our random decisions. Okay, and this is the place we're gonna leverage the fact that our samples are independent to arrive at this point. Okay. Now here again we have two terms. First term is identical to what we saw for gradient descent. Second term arises because our oracle is not perfect and the estimators have some variance. Okay. Again, we note the telescoping structure for the first term, and the fact that I can replace the function value at w t plus 1 with the initial suboptimality gap, and then we're going to arrive to this point. So this is a valid bound for all the step sizes that are strictly less than 2 over L. All that remains is to optimize this bound as a function of the learning rate. And you can do so, I would say, easily. But the calculation is a little bit more involved. Right? So I'm going to skip it in the lectures. But if you do so, you're going to be able to find the exact step size that we stated in the statement of the theorem. All right, so that's it. So we successfully proved these two theorems for the performance of the gradient descent and SGD on functions that are smooth but not necessarily convex. In the next lecture, we're going to talk about certain ways of strengthening SGD and its guarantees, if you will. I'll see you next time.